Organic chemistry. Start here. Now, if you want to, I put the crash course organic chemistry video. He does a good job. You've probably heard of crash course. It's about 10 minutes long. If you want to watch it as a help to reprocess this information, feel free. Definitely looking at like this big picture right here showing you lots of different ring structures and benzene rings and cool stuff here because the organic molecules can be quite large actually. We're going to of course stick with ones that are a little bit smaller to begin with because this is quite an overwhelming subject. I had to take 2 semesters of organic in college and ooh, very challenging, I'm just going to tell you. Organic chem is one of the hardest of the chemistries, and if you're going pre-med, you have to take organic. All right, so let's start talking about organic chemistry and organic compounds. Organic chemistry is the study of carbon compounds. That's our first thing to note. Now, in organic compounds, carbons are found bonded to other carbon atoms and that are nearby other carbon, carbon on the periodic table, like hydrogen, nitrogen, oxygen, sulfur, phosphorus. The halogens, these are all good examples. Just to clarify though, you want to look for ones that have carbon and hydrogens bonded together with other non-metals. That's a huge indicator that we're talking about something organic. There are compounds that have carbon in them that are not considered organic, like carbon dioxide. There is no hydrogen there. Calcium carbonate. Well, calcium's a metal, carbonate is a polyatomic ion. That one's obviously ionic. It doesn't fall into the organic molecule category. Sodium cyanide there, NaCN. Well, that has carbon in it, but no hydrogens. It also has the metal. So there's definitely ones, if they're ionic and have carbon, not really considered organic. Carbon dioxide and carbon monoxide, CO and CO2, don't really have the hydrocarbon thing going on, so they're not considered organic either. We would say they are inorganic. Stuff that doesn't, isn't just a bunch of non-metals like carbon and hydrogen and other stuff. That's pretty much what our bodies are made out of, is basically carbon, hydrogen, oxygen, and nitrogen. Those are the main components of DNA, the main components of proteins, carbohydrates. I'm sure you all remember this from biology last year when you studied those macromolecules like monosaccharides, disaccharides, amino acids, nucleotides, all of that good stuff. Most importantly, carbon is an interesting entity because it can bond to other carbons. It can form chains that are super large, 2,000 in length. These are what we would call these biomacromolecules. They are the molecules of life, of living things. So they can be super large. For our study, our little survey we're doing here, we won't be going that large though. Carbon has 4 valence electrons. What does that do for us? Likes to share the 4, can form 4 covalent bonds. That enables it to be able to do complex branch chains, ring-like structures. There's tons of possibilities. So like carbon can do the 4 single bonds, can do chains like that. It can do 2 singles and a double. It can do 2 doubles, and it can do a triple and a single. So with all these different arrangements, it can form different branches. It can form long, super long chains. It's very cool because of those 4 open ways of bonding, 4 different ways of bonding. So many different molecules could be built. So take a moment here based on our definition. Looking for carbon, mainly with hydrogen and other nonmetals, as to which one would be considered organic. Identifying whether it's organic or inorganic is something you definitely need to be able to do. So let's go through the top row. Would you say this one is organic? Has carbon and hydrogen, it's forming these rings. You see double bonds, you see single bonds. Is that organic? Definitely yes. Give that a check. How about this one? Is this organic? This middle one. No, there isn't carbon in it at all. This is actually ammonia, so this would be an inorganic molecule. So that's a no. How about over here to the right with our sodium positive, our chloride negative there? Any ideas on that one? That's a no. This is actually an ionic compound. That is sodium chloride or salt. And now looking down here, this one right here. 3 carbons, lots of hydrogens. Yes, this is a check. If we look at that one, 3 carbons with all those hydrogens, this is actually called propane. Propane is what you would find in the little tank underneath like your gas grill. It's used for like cooking on the grill. How about this one over here? Last one to the right. What do you say there? Is that organic? That's organic. It's got hydrogen and carbon and other nonmetals, so we would definitely do that. And yes, this is acetic acid. And acetic acid is something I've told you about before. That is the IUPAC name. We normally just call it vinegar. And vinegar, of course, is very important. We use it for lots of different things. We use it for cleaning. We use it on our food. It's in our ketchup. It's in lots of different recipes and things, but definitely an organic compound. So circle those ones. And that's one thing you would be able to ask to do is identify whether it's organic or inorganic. All right, looking here. Simplest organic compounds contain only the elements of hydrogen and carbon. We call them hydrocarbons. Hence the name. Hydro for hydrogen, carbon for carbon. Hydrocarbons. These ones are only going to have carbon and hydrogen. The most basic of the hydrocarbons is methane. Methane right here, CH4. That's what comes out of my gas outlets here in the classroom when we light the Bunsen burners. Methane is the main component of natural gas. It's a very good, fuel, okay? You know the Lewis dot structure you see up here. It's a tetrahedral shape, okay? Has the tetrahedral shape with the 109.5 bond angle. But this is the smallest, most simple type of hydrocarbon out there, CH4. We classify the hydrocarbons in 3 groups: alkanes, alkenes, and alkynes. Depending on the ending there, it's going to determine what type of bonds are in the chain. The first one, alkanes, we call them saturated. They only have single bonds between the carbon atoms. Single bonds between them. Now, this one is showing you 1 to 2 carbons here. This is called ethane. If you were drawing a Lewis dot structure, it would, not a double bond. It would have a single bond between it, and then it would have hydrogens filling in the rest of the octets. Okay, like so. And this would be ethane. That would be like the Lewis dot structure for it. You see the ball and stick model. If you look at the ball and stick model, it's basically 2 tetrahedrals stuck together. Very 3-dimensional. I don't know if you can visually see it, but like this would be one of the tetrahedrals. Then this would be the other tetrahedral here. So it's like 2 tetrahedrals have been stuck together. The key is, though, for alkanes, only single bonds, all hydrocarbons, but all single bonds. Alkenes, the ending changes to ENE. This ENE, because it has 1 or more double bonds. And you can see that here on the ball and stick model. We have a double bond. This is ethene. Okay, yeah, so this one's called ethane, by the way. ANE, as you can see, it matches the alkane. This one over here is going to be ethene. It changes the ending to ENE. And if you draw the Lewis dot structure, let me draw it over here. Draw the Lewis dot structure here. It's going to have only 4 hydrogens on it. And if you look at the shape, the way that this ethene looks, it's basically 2 flat triangles. You got 2 T-planars going on inside this molecule. So within the bigger molecule are the individual shapes that we've already looked at. All right, last one, alkynes. If the alkanes have single bonds and the alkenes have double bonds, what do you think is going to be different about the alkynes? Different group here. Last group. One has single, the second one has double. These guys, alkynes, yes, they have the triple bonds. Exactly. Okay? Alkynes have the triple bonds between them. And this one down here, I'm sure you could probably guess the name. If the first one's called ethane, because it has all single bonds. The second one's called ethene, because it has 1 double bond. What do you think this one down here would be called? Any guesses? Ethyne, exactly right. This is going to be ethyne. The ending just changes to Y-N-E, and it has a triple bond. And it looks like this. It's a nice linear shape. It's a straight line. You've got the triple in the middle and then 2 hydrogens on the end. It's a very linear shaped molecule. So that's the basic, very lowest ones of alkanes, alkenes, and alkynes, starting with 2 carbons. Now you can have 3 carbons, you can have 4 carbons. The chains can get longer, okay? All right, saturation versus unsaturated. Now, we just said that the alkanes are all saturated. Why are they saturated? And then the alkenes and the alkynes are unsaturated. Well, let's define what that means. Carbon chain is saturated when only contains single bonds between the carbon atoms. Each carbon is bonded to its maximum number of hydrogens. So it has its maximum number of hydrogens bonded to it. So we say it's saturated with hydrogen. So if it has all single bonds, like the alkanes do, it falls under the saturated category because it has the maximum number of hydrogens that could be attached. Unsaturated ones, like our alkenes and our alkynes, where there's a double bond or a triple bond, you could break those double or triple bonds and add more hydrogen. So that's why those would be considered unsaturated. The significant part, though, is the unsaturated ones are more reactive and more easily broken down, okay? So giving you a real-life example about this, we're going to look at like saturated fat versus unsaturated fat. So if it has a double or triple, we're going to label it unsaturated. If it's all single bonds in the hydrocarbon, you would call it saturated. So let's look at our table here. Real-world consequence of saturated versus unsaturated fats. And it applies here because in these molecules, okay, the ones that have all single bonds that aren't as reactive, they're harder for your body to break down, like, you know, the animal fat or the butter, the cheese, the cream. That's why if you don't exercise and your body's not totally up to a good thing, it can clog up the arteries and because it's not as easily broken down. The unsaturated fats, like your oils, the olive oil, canola oil, I personally like to cook with safflower oil now. It's really a light oil. I kind of like that one. These ones, of course, are considered good fats. They have double or triple bonds in them. And I'm sure you've probably heard of the omega fatty acids, the omega oils that are like found in fish oil and stuff. That's because they have like omega-3, 6s, and 9s. They have double bonds along those particular carbons in the chain. So, and of course, they're more easily broken down because they have the double or triple bonds where enzymes and things in your body can react and process them better. So this is a real life example of comparing saturated versus unsaturated in terms of fats. okay? All right, let's talk some naming here. Naming and drawing alkanes, and we're probably gonna, only get to a certain point, and then we're gonna have to finish this next class. So try to stay with me. It's gonna get a little confusing. All right, naming alkanes. There's a couple things we have to look at. We need to look at the order and arrangement of the atoms and the way that they are spaced. How are they attached? Are they just a straight chain? Are they a branched chain? How does it look? So there's a whole different grouping here when it comes to looking at writing out the formulas and the naming for different organic molecules. So for alkanes, we're going to stick with naming alkanes right now. This would be butane. Has 4 carbons in it. The prefix for 4 is but. We'll get to the rest of the prefixes, but butane is what's found in like lighter fluid. Now, it has 4 carbons and 10 hydrogens, noted by its formula right here. Well, look over here. Isobutane also has 4 carbons and 10 hydrogens in it. The difference is, though, isobutane, there is a branch in the center that's attached to the middle carbon. So it's not a straight chain, it has a branched chain, so it looks slightly different. And when it does those branching, sometimes they use the prefix iso with it. But these are considered to be isomers of each other. All right, why is that? Well, they have the same formula, the same number of atoms, but they have different structural patterns. One has a branch and one is a straight chain. So totally, gonna make it a little bit more difficult here by having to look at these branches versus the straight chains. All right, the purpose of naming branch chain alkanes are viewed from a straight chain standpoint, or the longest carbon chain. And then we might have some groups that are attached off of the branched chains. The parent chain is going to be the longest of the carbons. Counting the carbons in the longest chain. That's going to be our parent chain. After the parent chain, we have what we call substituent groups. And remember, these are all hydrocarbons, so if we're having substituent groups, that means they are attached instead of a hydrogen. So they're like substituting in for a hydrogen. And these are side branch groups that appear occasionally off the main the longest carbon chain there is. Now we'll be following the systematic rules of IUPAC, which is the International Union of Pure and Applied Chemistry. This is where the naming rules come from. The key here, though, and the hard part with organic is a lot of professors like to use the common names and don't necessarily follow the IUPAC system. And when you Google stuff, sometimes it'll be in a common name versus the IUPAC name. So it can be a tad bit confusing, but we're going to follow IUPAC. But just know if you start Googling, you might see other names for the same compound. All right, here is our nice chart that goes through the first 10 of the carbons. And we're only going to go up to 10. We're not going to go farther than 10 with this because it'll get too complicated too quickly. What you'll notice at carbon 5, the prefixes are the same. We have pent, hex, hept, oct, non, deca. Those ones are all the same prefixes that you're used to, the ones that we did in the covalent naming. For organic, the first 4 are different though. 1 carbon is meth, 2 carbons is eth, 3 carbons is prop, and 4 carbons is but. So those first 4 are different than the normal naming system where you would go with mono, di, tri, tetra. This is meth, eth, prop, and but for the first carbons. Then it starts at penta like normal. Here are the normal formulas, as you can see here. But because we're dealing with branch chains and chains, we usually like to do it as a condensed structural formula like so, where we're not writing out everything in the Lewis dot structure, because that would take forever. So for instance, let me show you propane here. If I drew the Lewis dot structure of propane, I would have to draw it like this. And this is how you should think about these condensed structural formulas, as groupings. This is how I do it. Like this part right here. This is a CH3 group, okay? 1 carbon, 3 hydrogens attached. Those are usually on the ends. In the middle, though, because it has to attach to 2 carbons in the middle, you're going to find the middle groups are all going to be CH2 groups because they have to attach to the 2 other carbons. And then, of course, this one over here is also on an end, like so. So this is going to be a CH3 group as well. So that's kind of how it looks, and it'll keep going, like, depending on how many carbons are in there. For instance, this is like 1, 2, 3, 4, 5, 6, 7. That's heptane. The first end has a CH3, the last end has a CH3. Everything else is in the middle. It's going to be CH2 groups, repeating CH2 groups to form, because they have to bond to either carbon on either side. Now the hydrogens, of course, complete the octets of the carbon. That's how you know how many carbons how many hydrogens to add around the carbons to complete the octet of 8, you know, having 4 covalent bonds. So we're going to go through a process of naming and start an example. I don't know if we'll finish it, but we'll start it. First thing we're going to do is find the longest chain. Count the atoms until we find the longest carbon chain. Second thing is we're going to start looking at the substituent groups, the ones that are branched off of the main chain. We're going to start counting them and labeling them. And of course, we're going to do it based on the lowest numbers possible for the carbons. We're going to name those substituents. We're going to attach the correct number to them, okay? And we're going to write out the name of the molecule. After we've done all this, we will list the substituents in alphabetical order. We will, for the ones that are identical substituents, we will use prefixes, although this is redundant in my opinion, but that's how the IUPAC naming system does it. And we will alphabetize them. Last but not least, we will use the correct punctuation. In this case, you separate numbers with commas, and you separate numbers and letters with hyphens, or numbers and words with hyphens. And then at the very end, you tack on the name of the longest chain. Okay, the parent chain goes on the very end of the name. This, of course, probably means nothing to you, so we're going to work it step by step through the problem. Before we do that, let's identify possible substituent groups. We're going to stick with the most basic. We're only going to do the ones that are up to 4 carbon chains. We know meth means 1, eth means 2, prop means 3, and but means 4. So these could be side branched chains off of the main chain. So if there's only 1 carbon, it's a methyl group. If there's 2 carbons, it's an ethyl group. If it has 3 carbons off of the main chain, it's a propyl group. And of course, if it has 4, it's a butyl group. Now you can write them one of 2 ways. You can use the formula like this, CH3 or C2H5, or you can do it, look at it from being a condensed structural one, because this technically is C2H5. There are 2 C's and 5 H's in there. Some people draw it like this, some people will just draw it like this. But both of them are considered ethyl groups because it's 2 carbons and the 5 hydrogens coming off of the main chain. So you can do it either way. You're going to see them written either way. So let's look at our big example here. The root name the longest continuous chain, this parent chain. So you kind of have to start counting from any direction to figure it out. We're going to look here, going to count. I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. I can go start down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I try to go this way, up this way, that's not going to get me to the longest chain, so that doesn't work. So you just kind of count and figure out which one is the longest amount of carbons in sequence. Well, I've come up with 10 here. So that means if I look at my list, 10 means it's going to be decane. This is going to be my root name because there's 10 carbons in the longest chain. So I'm going to put that on the side there. I have a decane. Now, which way do I number though? This is kind of the idea. Which way should I number? Got to look at that. Just a second. So we have decade. We have our root name. Now let's look at numbering. Number the chain, putting the substituent branches at the lowest numbered carbon. Well, if I'm looking here, I can start here, or I can start here to get to 10. So looking at that, this is going to be a branch. This is going to be a branch. Either this one or this one would be a branch, depending on how I number. So it makes more sense to get the branches off of lower number carbons if I start on the left. So if I start on the left, doesn't really matter which one I do. I'm just going to do this one because it's more in the straight line. This would be carbon 1, this is carbon 2, this is carbon 3. That means this branch is off of carbon 3. This would be carbon 4, carbon 5, carbon 6. So this one's off of carbon 5, this one's off of carbon 6, 7, 8, 9, 10. So that puts my branches off of carbon 3, carbon 5, and carbon 6. If I went the other direction, let's just do it hypothetically, and made this 1, this 2, this 3, this 4, this 5. Well, my first branch wouldn't start till 5. So I want to put them off of the lowest numbered carbon possible. So in lieu of that, I'm going to number from left to right in this case. It's not always going to be the case, but that's what I'm going to do. Now identify the substituents and give each number the C it's connected to. So this is 2 carbons. This is CH2, CH3. Is this a methyl, an ethyl, a propyl, or a butyl? Methyl, ethyl, propyl, or butyl. How many carbons off the main branch? This is only 2, so we would call this ethyl. And it's on number 3, so we would call this 3-ethyl. How about this one? It's 5. What? Methyl, ethyl, propyl, or butyl? This one's a methyl. Good. And this last one, this would be off the 6. This is also a methyl. Now this is where it gets to be a little tricky. We have 2 methyl groups. And this gets redundant. I don't know why they do this, but they do. Now we have to use a prefix because there's 2 methyl groups. We combine these 2 together. We call it 5, 6 dimethyl. The di meaning that there's 2 methyl groups. Redundant, I know, but it's the way they do the naming system. So I'm going to have my 3-ethyl. And I'm going to have my 5, 6 dimethyl. Those are my 2 substituent groups. So this is how I would set up this particular slide here. And we would get ready to write out the entire name.